So in a previous video, we showed you how to find the parametric form of a polar equation. And we're now going to use that form of the equation in order to find the derivative dy dx, but from a polar function. Now, the formula, I warn you, is going to be unattractive, but it is what we have. Now, recall from a video that we did on parametric derivatives, dy dx is going to be equal to dy dt divided by dx dt. And we're going to use this same representation, but now we're going to use this parametric version of the function. So essentially, remember, t has just been replacing theta. So our example here that we had was for the polar curve 2 cosine 2 theta, and we came up with this general relationship. And for that specific function, we replaced r in our r cosine t for x with r as a function of t times cosine t, and then r as a function of t times sine t for the y coordinate. And so it is these representations, or in more abstractly, these representations that we're going to use to derive this formula. So this is going to be a little messy because these are both functions of t multiplied by each other. So in the abstract, when we take this function, we're going to get a product rule, r prime of t, so in the derivative for t, times sine t. Yeah, sine t. Text is bugging me. And then the other half of the product rule will be r of t, and then the derivative of sine is cosine t. Now, in the denominator, the derivative for x, again, we're going to base on this. It's going to be r prime of t cosine t, and then plus r of t, and then the derivative of cosine is actually minus sine, so minus sine t. And this is actually our general derivative for calculating polar coordinates. And if we convert everything back to thetas, then we end up with the function, the formula that you will see given in most textbooks. And again, some textbooks won't even bother to derive this. But this is where it comes from. So one advantage of having seen how this is derived is that it actually means you don't need to memorize it. You can, in fact, just remember the polar or the parametric version and then know how to convert a polar form into a parametric form. And then you just use the general parametric version of the derivative to obtain this result. It is still going to be ugly, but at least you won't have to memorize this formula. Now, if you like memorizing things and you don't really care where it comes from, then that's also fine. You'll get the answer as long as you do all the arithmetic correct. Now, in order to apply this, we're going to do one worked example just so that we can see how it works. And I am going to use the polar form that we had earlier for our example, this one. Now, again, if we apply this dy dx formula, so the derivative of this by this prime, we're meaning the derivative of the only variable that's in the equation, which is theta. So in this case, our numerator, the derivative of this with respect to theta, we're going to get another 2 come out, and this will be another, and it'll turn negative, sine of 2 theta. Cosine becomes negative sine, and then times sine theta plus the original 2 cosine 2 theta times cosine theta. And then in the denominator, same components, but rearranged. So we still have negative 4 sine of 2 theta. But now it's times cosine theta minus the original 2 cosine 2 theta times sine of theta. And then if you were to evaluate this at a specific point, let's say evaluate the derivative at, let's say, theta is equal to pi over 4. Maybe make our life a little bit easier since twice pi over 4 will be pi over 2, and we'll get ones instead of, or zeros instead of crazy things. Then our function, let's see, this would become pi over 2, and this would become pi over 2, and this would become pi over 2, and pi over 2, and then this would become our pi over 4, and pi over 4, pi over 4, and pi over 4. And if we evaluate that, let's see, sine of pi over 2 starts at 0, goes to 1. That's going to be negative 4 times 1. And then sine of pi over 4 is going to be 1 over the square root of 2. Plus cosine of pi over 2 is going to be 0 because it starts at 1 and then it goes to 0. And then in our denominator, again, we're going to get negative 4 times 1. And then cosine of pi over 2 is also 1 over the square root of 2. But then minus 2 times 0 again. Again, this is why I picked pi over 4 to make the math a little easier, because if you pick something like pi over 3, then you just get crazy stuff all over the place, because twice that is still more fractions. Nothing cancels or simplifies. So it looks like we're going to end up with 1. Again, the exact how simple this turns out to be is going to depend on the specific function and the specific value on the function that you choose. This one turns out to be relatively simple. If you look at the graph of the function, you can actually see why that would be the case, why this would actually be just a nice simple thing. It's the end of a pedal, turns out to be nice. But again, if you choose any other random point along the function, you're going to get a fairly unattractive result that's going to not simplify and still have square roots in it and everything else. Now, usually textbook problems do not have you go any further than this, so they don't have you then come up with the equation of the tangent line. If you did have to do that, you would have to take your theta value, plug that in to the function, and convert the r theta combination back into rectangular coordinates in order to then draw the equation, find the equation of your line. And that's very complicated. And again, most textbooks in the main bulk of the section will not ask you to do that. You just have to remember the formula or know how to derive it and then plug in the pieces and then do a little bit of algebra to simplify.